basically volumes when we talk about volumes, I guess there's variety of different situations that we look at. One situation we look at is something called a cylinder. Actually, let me break it down slightly differently. I'm sorry. Sorry. Okay. I'm going to break it down like this. Volumes, we can first break it down into two types. One type is what I call cross-sectional area. And the other type is what we call the cylindrical method. So this is section 5.3. We're going to do this on Monday. Okay. I would say the cross-sectional area ones, those break down into three different types. The first type is called cylinders. The second type is called discs. And the third type is called washers. Now, the cylinders, when you look at a cylinder doesn't necessarily have to be a circular cylinder. So like a circular cylinder looks like this. Circular cylinder kind of looks like this. Looks like a can. And what happens is when we do this cross-sectional area method, you can imagine that you have an axis running through the center of your object. So in this case, it might look something like this. And then if you kind of cut up perpendicular to the axis, you get these little cross-sectional areas. So, we cut up perpendicular to this axis. And when you do that, you're going to get these circular discs like this. And the volume of this circular disc is equal to the, or actually, sorry, I mix. Let me back up. Your cylinders in this class don't necessarily have to be circles. They could be something like a triangular type cross section. So it could look something like this. Does that make sense? And then when you look, you have this sort of, you have some sort of line that acts like an axis, and it kind of runs along the object. So maybe I could draw us a picture that looks like this. And you still cut it up perpendicular to the axis. Does that make sense? So you could really have any kind of shape, but when you're looking at these guys, the cross-sectional area, the volume for these guys here, the volume is equal to the cross-sectional area times a little bit of thickness. Okay. So the way that we write this is we call the cross-sectional area A of X, and that little bit of thickness we call delta X. Like that. So in the circular cylinder case, the cross-sectional area is a circle, and then you have that little bit of thickness, and that little bit of thickness looks like this. So it's like a coin, a very thin coin. Okay. And in the sort of triangular thing, do you guys eat Toblerone? You know that chocolate Toblerone? If you look at the box, it looks just like this. It's like a triangular box. In that case, the cross-sectional area would be a triangle. And then that little bit of thickness, you know, maybe it looks like this. And then that gives you a little triangular wafer. And this is sort of one slice. So what we're going to do is we're going to chop up perpendicular to this axis, and you're going to get a whole bunch of coins, or you're going to get a whole bunch of triangles, and then we're going to add them up. Okay. So this is just the volume of a small piece. So the volume of the whole thing is going to approximately be equal to the sum of all of these little discs or all of these little triangular wafers. So if I took my A of X times delta X, and then I added up n of them. Sorry, let me move this. If I added up n of them, that's an approximation for the total volume of this thing. Now, in principle, this cross-sectional area should depend on what your X value is. And that dotted line is kind of representing our X-axis. Okay, so you could pretend that this is like the X-axis. This is like the X-axis here. So let me draw one more example, actually, to illustrate the importance of this, knowing what Xi is. Let me draw one more picture. Let's say you have something that looks like this, a cone. This this cone is something else that we can find the volume of. So you can imagine that you have this, your axis kind of goes through like this. And can you guys see that as you move along the X-axis, your area is getting, the cross-sectional slice is kind of growing. It's getting bigger and bigger, right? So it's sort of like you have very, very small coins on this side, and you have very large coins on this side. And then we add up all those coins to get an approximation for the volume. Does that make sense? So what we're going to do is we're going to chop up perpendicular to the axis of running through there. And when we chop this guy up, your coins kind of look like this. So if you wanted the actual volume, what you would do is you would take the limit as the number of discs goes to infinity. So you're making each little triangular wafer or each little coin, you're making them thinner and thinner because the number of coins is growing bigger and bigger. So this is just like our idea for the Riemann sum. And oops, this is too soon. So then this guy, so our volume is actually going to be equal to the limit as we let n go to infinity. And what this leads us to is an integral. So you'd have to indicate what your starting point and ending point of your x values are. And then you just integrate the cross-sectional area. Okay, so this is the basic idea for this cross-sectional area situation. Now, in 5.2, I'm not going to focus on the cylinders case so much. I'm going to focus on the discs and the washers case. So the discs case is like this. And the washer case looks a little bit different. So what would be a good example of the washer case? There must be some sort of a candy. Michelle, maybe you know. There must be some sort of a candy that's like circular, but has like a filling on the inside. I'm drawing a blank here. Anyways, like a Lifesaver, Reese's, Rolos. Rolos would be a good example. I'm just going to use Lifesavers. Lifesavers is the closest. Donut almost works. Yeah, let me use Lifesavers. So the washer situation is really common. I mean, it's really similar to the disc situation. The difference is that you have a hole in the middle. So for the washer situation, it looks something like this. Now, this is the most simple washer situation. Okay, not every problem looks like this, but this is what the washer guy kind of looks like. So we're still going to do the same thing. We're still going to chop up perpendicular like this. And we're still going to have that we're still going to have that axis going through like that. But this time, when you chop it up, instead of having a circular disc, you're going to have a something that looks like a washer. Now, I don't know if you guys know what a washer is, but I should have one handy, but I don't. Basically, when you have a screw and you want to tighten the screw, let's say against some piece of wood, a lot of times I'll put a little metal circular disc with a hole in it. And then that sort of distributes the pressure. So then the screw pushes against the wood, but it doesn't damage the wood. And also it's kind of distributes the pressure. So if I were to draw a picture of a washer kind of looks like this. It's like a hole. It's like a disc with a hole in it. Like that. So this is our washer situation. Okay. So both of these are special cases of this guy. Okay, just special cases of this. So what we're going to do is we are going to have a couple of different volume formulas. So let me write these down for you. Volumes with disks. The volume is just going to be equal to the integral from a to b dx. If you think about the cross-sectional area of a circular disc like this, that's just a circle, right? So the area of a circle is pi r squared. And the tricky part is figuring out r. So this is the tricky part. It's not that tricky, actually. It's usually just a function. Okay. And the volumes with the washers, this one looks like this. It's the integral from a to b. We're going to have pi r big squared minus pi r small squared dx. And again, the tricky part here is figuring out what r big and r small should be. Okay. So I hope this makes sense, because I mean, this is the area of a circle formula, and we're taking the area of a circle times a little bit of thickness, right? Area times a little bit of thickness, circle, circle. This is a circle with a hole in it. So when you look at this area formula, how do you describe the area of a circle with a hole in it? Well, you take the area of the big circle and you subtract the area of the small circle. So none of this is surprising. Now, what are we actually doing? Let me give you some examples, just with some pictures, and then we'll look at the worksheets. I want you to imagine that we have a curve that looks like this. Okay, so this is the x-axis, this is the y-axis, this is A, this is B. My function here is y is equal to f of x. And what we're going to do, we're going to take this curve and we're going to rotate it about the x-axis. And can you guys imagine what type of an object we're going to have when we rotate this curve about the x-axis? This is called a solid of revolution. Do you know what that object is going to look like? Does anyone want to type in the chat box? The very famous object you see every Sunday or Saturday. But here, it would be a sphere if I drew the curve that looked like a semicircle. But yeah, it would look like a football, like Steph says, and Michelle and Jason. I don't know if you're, American football, not the beautiful game. So your 3D object kind of looks like this. Oh, shoot. Okay. Kind of like that. And what we're going to do is we're going to chop it up perpendicular to the axis of rotation. So chop up perpendicular to axis of rotation. And then that's going to go like this. Oh no. Right. And then so this looks like, I'm trying to make it look 3D. That's why it's curved. So this is definitely discs, right? Like when we look at this, we could see that if you took a piece of this cross-sectional area right here, and you were to pull it out to the side, it would look like a circular disc. So earlier I had told you that this formula over here is pi r squared. And what would r be? R would be this, the length of this distance from the x-axis to the curve. So in this particular case, if I were to look, oops, if I were to look at the radius of this guy right here, the radius is actually equal to just f of x. So when I go to write down the volume would just be equal to the integral from a to b pi times f of x squared dx. Okay. And that's kind of how the disk method works.